Okay. Next topic is number 3, unit 1 compartment open model. One compartment open model. Seema, you just concentrate more and more on this topic. This is the very most important topic in your final exam point of view, and also this is a very small unit. You have only 2 topics in this unit. Once you go through the syllabus, then you can find out it. And one more important thing for this one compartment open model, you have derivations. So everyone has to write. And one more important thing, in the second unit, already you have some idea regarding compartment models, right? I told you the compartment model types and all, and you know the pharmacokinetic parameters names AUC, Cmax, and Tmax. Like these parameters also you know. So this is all about your second unit. So you must remember while reading this one compartment open model, all these parameters, PK parameters, what are those, how we will analyze it, and what are the denotions for that pharmacokinetics, AUC means what, Cmax means what, like that. So next one is one compartment open model. From this name, you can get something. Open model. Why it is called like that? Open model. Seema, this one you have one compartment open model and multi-compartment open model is also there in the fourth unit. So what is this all? See, these all compartmental analysis should be based on the assumptions. We cannot predict that these are happening correctly or directly. These all are assumptions. So you must follow what they have given. See, this is one compartment and this is multi compartments. Multi means more than one. Either it may be 2 or 3 or 5. So this is of fourth unit, right? So under third unit, you have one compartment open model. The basic assumption of this model is assumed that our body is single uniform compartment, single uniform compartment. So generally in some compartmental types, what they told us, you have multiple organs. So you just assume that each and every organ is like one compartment. But here our total body unit is consisting of single uniform. This is of one compartment, total one compartment. In this total one compartment only we are going to do IV infusion, IV bolus, or whatever it is the dosage form. But you can remember that one compartment open model is our body is assumed as a single uniform compartment, right? And then what is the basic phenomenon for this one compartment open model? I will tell you. This is of also called as instantaneous distribution model, and the contents which you are going to read under this third unit is intravenous injection. This is also called as bolus, IV bolus, intravenous injection. This is the most important question. And then intravenous infusion. So you have 2 different kinds of routes of administration. You are going to read under this one compartment open model. See, this is the simplest way to describe the drug distribution and elimination. Here they are mentioning only 2. What are those? Drug distribution and elimination. Then what about absorption? Why they are not mentioning this absorption? Why? Because this is a rapid process. Which one? IV bolus or IV infusion? There is a negotiable or negligible absorption is there. because once the drug will enters into our circulatory systems, the process will be having some rapidity. So there is no absorption or negligible absorption. That's why in case of one compartment open model, so you have IV bolus injection and IV infusion. So you must neglect this absorption. So that's why this is the way to describe only the distribution as well as the elimination which will be happening in the body. So the major assumption of this compartment is the drug entry, that is in, and the drug exit, that is out, from the body is open model. The body acts as single uniform compartment. These two are the most important points. Okay, so that's why the body acts like a single and uniform. And then this one compartmental analysis is having following assumptions. See, the body is like single homogeneous unit. Then it doesn't have any barriers for the movement of the drug. You just assume that your body is like a single homogeneous unit, so that there is no barriers for the movement of the drug. So this model applies only for rapid distribution of the drugs. This model applies only for rapid distribution of the drug. So the drug entry and exit will be a dynamic process. And one more important thing here, the elimination will follows the first order process, that is concentration dependent. The elimination will follows the first order process. This compartment does not predict the actual levels of the drug in the tissues. See, this model does not predict how much amount of the drug will be available in the tissues. In the sense of actual levels, it cannot be predicted, but it will assumes the total changes of the plasma levels. Okay, it cannot be calculated the cumulative amount of the drug levels which will be available in the tissues. Okay, but it can be assumed that the total changes in the plasma levels. Okay, when your drug will be entered into either of tissues or organs, so it will be assumed that the total changes will be happening in the plasma levels of the drug is directly proportional to the tissue drug levels. So the plasma levels of the drug is directly proportional to the tissue levels of the drug. And one more important thing, in case of this IV bolus administration, once the drug will be enters into the body or circulatory system. The drug will be enters into the body or circulatory system. So in this the process is very rapid. And then once the drug will enters into the circulatory system, the organs or tissues will uptake the drug, then the depending parameter for this drug uptake will be based on the lipophilicity and molecular weight of the drug. And one more important thing, the binding affinity of the drug. The binding affinity of the drug. See, ma'am, when you take this IV injection, okay, when you take this IV injection, the drug will rapidly enters into the systemic circulation. After it enters into the systemic circulation, some organs or tissues will uptake the drug. So how much amount of the drug will be available in the particular tissue and the capability of the tissue to engulf that circulatory system drug, it will be totally dependent upon the lipophilicity of the drug and the molecular weight and how much of the drug binding affinity is there. I think you already studied under protein binding, drug and protein binding. So each and every drug is showing some binding capacity, either it may be to receptors or ligands, or they have some interactions with other drugs. So okay, so these three parameters will be very important for the uptake of the drug to organs or tissues. So this will be governs this uptake of the drug to the tissues or organ will governs you the VD. So how much volume of the drug will be distributed under particular concentration of drug levels. So in which organ or tissue is having more volume of distribution and all. So once the drug will gets entered into the organ, then only you can justify it. Either it may be having some volume of distribution in the particular organ or not. So if it is not be enters into that organ or tissue, so how can you justify that? So this is also one of the important parameter in this IV bolus administration. So the uptake of the drugs will be totally dependent upon these parameters. So once the drug will enters into the circulatory system, then this circulated drug will be uptake by these organs or tissues. So this process will governs you the VD as well as the KE. What do you mean by KE? Elimination rate constant. That means it includes metabolism and excretion. So here it will governing you the distribution of the drug. There is no absorption. See here, the volume of distribution will says you about the drug distribution capacity. And in case of KE, it includes the metabolism and excretion. It is K capital E, not a small e. If it is K small e, if you write this K small e, it will undergo excretion. And if it is K capital E, it is elimination. These are very important. And then the term indicates that the input, that is input is nothing but the availability, that is the entry of the drug, and output is nothing but the elimination, that is K capital E, are unidirectional, and that the drug can be eliminated from the body. Each and every word, every sentence is most important. See here, here is your drug, and once your drug is entering into the circulatory system, that is blood and other body tissues. See, this input is nothing but Ka, that is of absorption. In our terms, input is absorption and Ke is output, that is elimination. So this elimination will includes metabolism and excretion. See, once the drug will enter, then the drug will be exiting. See here, but here in case of IV bolus injection, you don't have this absorption phenomena. Only the rapidly eliminated or rapidly distributed drugs will follow this kind of kinetics. So that's why there is negotiable absorption is there. And this is the most important question, that is one compartment open model by intravenous bolus administration. This is all derivation part, ma. So before learning this, you have to remember only 2 points. This IV bolus administration will be governing you the volume of distribution and Ke. This volume of distribution will includes your distribution phenomena. So you have to learn these two parameters very clearly. And one more thing, this compartment will based on the assumption of our body is like a single uniform compartment. You just remember these 2 points. See what it is telling. In case of IV bolus administration, when a drug distributes rapidly, only those drugs will follow this kind of kinetics. This distributes rapidly in the body is given in the form of rapid intravenous injection. It takes only about 1 to 3 minutes for complete its circulation. So see how much rapid it is. It will take only about 1 to 3 minutes time to complete entire circulation, and therefore the rate of absorption is neglected in calculations. See how clear it is. Okay, so only the rapid distributed drugs will follow this compartmental kinetic model, and this will take only 1 to 3 minutes to complete its entire circulation. So that's why you have to neglect the absorption in the calculations. So then from this point onwards, your calculation is going to start. dx by dt, this is the rate of your drug distribution. Okay, this is rate in minus rate out. In is nothing but your availability, nothing but your absorption, and rate out is elimination. So here you are neglecting the absorption. Then since rate in or absorption is absent in IV bolus, then the equation will becomes. So then what is the next equation? dx by dt is equals to only rate out, that is minus rate out. Rate out is nothing but Ke. Ke is of your elimination. So then this dx by dt is directly proportional to the amount of the drug present in the plasma. Amount of the drug present in the plasma. Present in plasma. So here why you have written this amount of the drug present in the plasma? I already told you the uptake is totally dependent upon the organ or tissue capability, whether it is accepting the lipophilicity of the drug or it will be accepting the molecular weight this much only, less than 100 daltons or 200 daltons. This will governs, this will, the organ capacity will governs you how much amount of the drug will be available for its distribution and elimination. So for that reason, dx by dt is equals minus rate out. Minus is very important here. Rate out is nothing but Ke. So this rate of this drug distribution is directly proportional to the x. So how much amount of the drug is distributed, that will be dependent upon the amount of the drug will be available in the plasma. This is the proportionality. This is not alpha, this is like proportional. Okay, so this is equation number 3. After that equation number 3, everyone knows that when you remove this this proportional, you will get some constant. So that constant is elimination rate constant. Okay, so when you remove this proportionality symbol, you will get some constant, that is of your elimination rate constant. If the rate out or elimination will follows the first order kinetics, then the equation will becomes dx by dt is equals minus Ke into x. Ke is the first order elimination rate constant and x is the amount of the drug in the body at any time t. This is remaining to be eliminated, and negative sign indicates here that the drug is being lost from the body. Why? This is the elimination process. Your drug is going to loss from the body. So that is what dx by dt is equals minus Ke into x. So estimation of parameters. This is the basic equation of this one compartment open model IV injection. So how you will estimate the parameters? By using this IV injection. For a drug that follows one compartmental kinetics and administered as rapid injection, the decline in the plasma drug concentration is only due to the elimination. So after some time there is a declining in the plasma drug concentration. So why this plasma drug concentration is declining here? Because the drug is going to be eliminated. So the declining of this plasma drug concentration is due to this elimination of the drug, not due to the distribution of the drug. Okay, so once there is a declining of the plasma drug concentration, you just remember that is because of the elimination phase, that is not due to the distribution. And then this elimination phase can be characterized by 3 parameters. This elimination phase can be characterized by 3 parameters, that is elimination rate constant, elimination half-life and the clearance. So when you want to write this IV bolus injection, you have to explain all these things and including this elimination phase characterization. So you have to write elimination rate constant, elimination half-life and clearance. So here you are going to find out the equations from the dx by dt is equals minus kex. From this equation, you are going to find out all these parameters. So first one is elimination rate constant. So first all of you should write dx by dt is equals minus kex equation. So then when you integrate, these slides will consisting of you the direct equations. So for that here I am going to derive you integration of the above equation. Then you will get integration from 0 to t dx by dt is equals integration from 0 to t minus ke into dt. So this is a constant. Then this in x 0 to t is equals ke minus ke into t 0 to t d. Okay, integration from 0 to t dx by dt is equals integration from 0 to t minus ke into dt. When you integrate this basic equation, you will get this equation. After that, then the equation will becomes in x 0 to t minus ke t to the 0 to t. Then you will get this equation in x is equals, sorry, in x here minus in x naught is equals minus ke into t. Okay, t minus 0 here, t minus 0. Then in x is equals in x naught minus ke into t. So you will get this equation. See here. The directly they are writing in the textbooks also directly integration of the above equation or the basic equation. So you did not understand properly. Okay. So if you have write like this pattern, then it is very easy to derive. So this is of your final equation for this elimination rate constant, where x naught is the amount of the drug at time t0. X naught is the amount of the drug at time t0. That is the initial amount of the drug injected. That is the initial amount of the drug injected. Then in the exponential form, this will be looking like same your first order kinetics, right? So then you have to integrate this equation. Then, sorry, exponential form. Then it will becomes x is equals x naught into e to the power of minus ket. First you write this equation. The next line you write down exponential form of the above equation. Then you will get x is equals x naught into e to the power of minus ket. Then it will shows the deposition of the drug will follows one compartmental kinetics is mono exponential. Mono exponential. The deposition is nothing but which parameters will includes in the deposition? Deposition. It will includes the distribution, metabolism and elimination. So from this equation you will get one point like the this elimination rate constant. In the elimination rate constant of one compartmental open model kinetics, the drug deposition process will have mono exponential. The departmental kinetics will have mono exponential form. X is equals x naught into k to the power of minus ket. So then you have to do log for this equation. I already told you in the zero order kinetics, we are calculating elimination rate constant. Elimination process is following your first order kinetics. So for that, the equations are similar to first order reaction. Then after writing this mono exponential equation, then you have to write down the logarithmic form of this mono exponential equation. Then you will get log of x is equals log of x naught. After removing this exponential, you will get one constant number, that is minus ket divided by 2.303. Okay, so then you convert this exponential form to the logarithmic form. You will get this equation, log x is equals log x naught minus ket divided by 2.303. And then it is very difficult to determine directly the amount of the drug available in the plasma. X is the amount of the drug available in the plasma. X naught is the initial amount of the drug at time t is equals to 0. So this will be available at time t and this will be available at time t naught. So it is very difficult how much amount of the drug will be available in the plasma. So for that reason, we will take consideration into the volume of distribution. So there is a relationship between the x is equals to Vd into C. Then Vd is equals to x by C, you know, right? So in this equation, you have log x is equals to log x naught. So when you want to determine total amount of the drug available in the plasma is difficult. So for that reason, you may consider to determine the volume of distribution. For that particular organ or tissue, the drug will be available. How much amount of the drug will be available in the particular organ or tissue. So for that reason, you can utilize here the volume of distribution. So what is the relationship of the amount of the drug and concentration of the drug with volume of distribution? Vd is equals to x by C. See here I written x is equals to Vd into C. Then this is one relationship. We can utilize this relationship to find out the amount of the drug available for organ or tissue. So see here, since it is very difficult to determine directly the amount of the drug available in the body, so then you just take an advantage. There is a constant relationship between the drug concentration in the plasma and x. Thus you can calculate the volume of distribution. It is a pharmacokinetic parameter, this one Vd. It is a pharmacokinetic parameter that will permits you the use of plasma drug concentration in the place of amount of the drug in the body. So then your equation is log C is equals to log C naught minus KET by 2.303. Instead of x naught, you just keep C naught. This is concentration of the drug in the body. So amount of the drug in the body we are not determining, only the concentration of the drug in the body. So the elimination rate constant is directly obtained from the slope of the line. See here how the elimination rate constant is obtaining from these plots. This is a regular plot or normal graph and this is a semi-logarithmic graph. So the Cartesian plot graph follows one compartmental kinetics and given by rapid IV injection. See how the graph is like this. So here you need to have T half, and when you plot the graph between time versus concentration, this is a normal graph. Here you are unable to find out the logarithmic values. I already told you. And by the utilization of this semi-logarithmic graph, you can able to find out the log values. Semi-logarithmic plot of the rate of elimination in a one compartment open model. Here the slope is Ke by 2.303 and here this is the initial concentration of your drug. See log C naught. This is the initial concentration of the drug and this is the concentration at time T1 and this is the concentration at time T2. So here you have some readings 1, 2, 3, 4. This is of timings and this is of log concentrations. So from T1 to C1 and C2 to T2. So between the time of for this T2 and T1 you have a T half. So you need to find out the T half life, right? So then elimination half life. So I already told you this half life also in case of first order kinetics. So the derivation is same to that of first order kinetics. Elimination half life. What do you mean by elimination half life? It is also called as the biological half life. So this is the oldest and the best known of all the pharmacokinetic parameters. It is defined as the time taken for the amount of the drug in the body as well as in the plasma concentration. See the definition carefully. Amount of the drug in the body as well as the plasma concentration of the drug. It will be declined by 1/2 or 50% to its initial value. So it will be expressed in hours or minutes. So the half-life is related to the elimination rate constant. So here they written directly T half is equal to 0.693 by Ke. So Ke is elimination rate constant. So how you will get this equation? I already told you in first order kinetics. Log C0 by C is equals to Kt divided by 2.303. Here C0 by C is equals to 2. Then T is equals to T half. Same equation here also. Then you will get log 2 is equals to Kt half divided by 2.303. What is the value of log 2? 0.3010. Derivation is same. Then T half divided by 2.303. K into T half is equals 0.3010 into 2.303. This value is 0.693. So here you want T half. T half is equals to 0.693 by Ke. This K is here Ke. For each and every time you need to write Ke, don't write K. Okay, Ke is elimination rate constant. Here we are talking about elimination, right? So for that you have to write elimination rate constant. This half-life derivation is same that of first order kinetics. Okay, so this is of elimination rate constant and then elimination half-life. From the one compartmental IV bolus injection, we need to find out three pharmacokinetic parameters. First one is elimination rate constant and the second one is elimination half-life and the third one is clearance. Okay, so how you will find out this clearance? See here, clearance is one of the important parameter. It will be defined you as the theoretical volume of the body fluid which is containing drug from which the drug is completely removed at a given period of time. So it will be expressed obviously in ml or minute or liter per hour. So how the relationship of this clearance with that of what is that elimination rate constant, right? See here, and in the your textbooks directly they given this equation. Clearance is directly proportional to the rate of elimination divided by plasma drug concentration. See how much amount of the drug will be eliminated out. It will be dependent upon the availability of the drug in the plasma. So for that reason, your clearance is directly proportional to the rate of elimination, that is dx by dt, and the plasma drug concentration, that is C, and clearance is CLT, total clearance. So the derivation for this clearance is, it is not available in your textbooks. One more time I am telling you. And rate of elimination dx by dt is equals, this is rate of elimination. Elimination is directly proportional to the C, that is plasma drug concentration. Plasma drug concentration. So here you are going to find out clearance, right? By removing this proportionality, you will get one constant. Then dx by dt is equals CLT. Here the CLT is a constant. This is a constant into C. Then you need to integrate this equation. Integration of the above equation from 0 to t. Sorry, from 0 to infinity. From 0 to infinity. Why? Here it is not 0 to t. From 0 to infinity you need to calculate. Why? This is a clearance. The drug is being eliminated out of your body, eliminated from your body. So for that reason, how much time it will be staying in your body. So you cannot assume that. So that's why there is a infinity time or infinity plasma drug concentration. So that's why there is an infinity, 0 to infinity. That is dx is equals dt into 0 to infinity c. Sorry, here it is CLT into CDT. See ma, here once again I am writing dx by dt is equals CLT. This is small l into C. Right? When you integrate this equation from the infinity, because of elimination you need to write infinity. Dx is equals constant CLT, integration from 0 to infinity. Then you have C into you have dt. Then then total total amount of drug eliminated, total amount of drug eliminated is CLT is equals AUC into 0 to infinity. Why I written AUC into 0 to infinity? One equation is there. Integration from 0 to infinity C into dt is equals to AUC 0 to infinity. This is one derivation is there for this also. So you have to remember, wherever integration of C into dt, this part integration of C into dt will becomes AUC 0 to infinity. Okay, this is of, instead of writing this C into dt, this is AUC into 0 to infinity. And one more important thing here, in case of clearance, why we need to write AUC? See here, how much amount of the drug will be available in the total area. See here, this is of total body area. Just assume like that. So the total amount of the drug will be available under this AUC only. So here you need to calculate the clearance, right? So for that reason, you have to take consideration into AUC. This AUC will tell you total amount of the drug will be available under the curve. So under the body, curve is nothing but under the body. So for that reason, to find out a clearance, you need to calculate this AUC in 0 to infinity. So here, see, concentration of the drug in the plasma into dt is equals to AUC into AUC 0 to infinity. So then the CLT is having one formula, total amount of drug eliminated, total amount of drug eliminated divided by AUC 0 to infinity. See, CLT is equals total amount of drug eliminated divided by AUC 0 to infinity. So the next equation is CLT is equals to X naught. Why here X naught will come? 0 to infinity. See here. What is this? Total amount of drug eliminated. So that's why here X naught will comes here. So X naught divided by AUC 0 to infinity. And what do you mean by X naught? One equation is there. X naught is equals VD into C naught. So CLT is equals VD into C naught divided by C0 by KE. One equation is there. AUC 0 to infinity is equals C0 by KE. This is okay. First you write down CLT is equals to VD into C naught divided by C0 by KE. Since AUC 0 to infinity is equals to C0 by KE. So here C0 will get cancelled. Then the final equation to find out your total clearance is VD into KE. This is C0 by KE, no? So this will get up. VD into KE. This is the final equation to find out your clearance. So to find out the clearance, which parameters you need? Volume of distribution and elimination rate constant also. There is an interrelationship between elimination rate constant, elimination half-life and volume of distribution. So the IV bolus injection, when you take this IV bolus injection, you need to consider only the rapidly distributed drugs. That is the important point, and you can assume your total body as a single uniform compartment. So in that single uniform compartment, you need to calculate elimination rate constant, elimination half-life and the clearance.